Awesome. Well, everyone, I want to welcome you to me and Sudha's talk on demystifying Hudi, a deep dive into Hudi's core. Hudi goes beyond just a table format. It's actually a full-blown platform filled with services and data management tools to help efficiently ingest, manage, and query data. So our goal for this talk is to give you a better understanding of its capabilities and its vast potential in real-world scenarios. And we'll dissect its core architectures by talking about a few things, explore its unique features, and hopefully we can talk about the differences in trade-offs between batch architecture and incremental architecture. So there's so much to cover, so let's go ahead and get started. We already did the intro, so I'll kind of skip over this part over here, and we'll dive straight into the agenda. So we'll have an overview of the Hudi platform, and then from there, we'll do a couple deep dives into Hudi services and features. And then I'll cover the differences between the batch and incremental architecture, and then finally tie in the incremental architecture back into Hudi and some of the concepts we talked about. And then we'll talk about distinct features that Hudi offers compared to other projects. So I want to kind of take a step back and talk about how Hudi was born before we get into the platform overview. So Hudi was developed in Uber in 2016 to address inefficiencies across ingest and ETL pipelines during its hypergrowth stage. So during this time, Hudi was dealing with petabyte scale data. So if you walk through an example of like a life cycle of a ride or an Uber ride, a rider requests a rider is in transit with the ride, and then finally a rider ends a ride. But throughout this single trip entry and a trips table, you can have many updates throughout this life cycle of the trip. One example is if like you tip 2 days later, right? This is the example of how some of the things can you have to deal with like late arriving data and stuff. So before Hudi was created, large Spark jobs were used to periodically rewrite entire data sets of Apache HDFS to absorb upstream online table inserts, updates, and deletes, and then reflecting the changes in the trip statuses down. This process was not only inefficient, but also very hard to scale. And so how do you bring like transactional guarantees to a data lake where you're storing like petabytes of data? And how can you efficiently and effectively work with streaming sources where you have to handle, for example, high influx or high bursty writes and late arriving data? This was essentially the inspiration behind Hudi. And so in the bottom, I have an architecture diagram that kind of talks about a high level overview of what Uber was kind of dealing with. And basically, they had to do full recomputes every so many hours in order to update their downstream tables. So the motivation behind Hudi was a couple of things. One, they needed fast analytics. They needed to power faster and fresher, not only internal-facing analytics, but also user-facing analytics as well. And the other thing that was a big deal was late arriving data. So not only did updates just go beyond the current date, it can span to months, right? And with a data lake, you would need to rewrite the whole table of partition just to do that. So this was the motivation and the challenges Uber was dealing with. And so specifically with Uber, they had a database and they scraped the logs to Kafka and built a replica coaster to a warehouse using an HBase table. The HBase is essentially like a read-up replica of their upstream database. So Uber took snapshots of the replicated HBase table to a Parquet file format, and then downstream consumers recompute their own derived tables based off of that. But the problem that they were experiencing was this recomputation. They were hitting capacity. So in January, one of the things there's a resource at the later of the slide that has been notes talk, but basically in January, Uber was running these 5-hour incremental, doing these updates basically, but they were throwing hundreds and hundreds of executors to do that. By August, they were redlining, where they're throwing thousands of executors, and in the processing the whole pipeline was taking 10 hours plus. So they were already redlining. So because this was happening because as the snapshots grew, and as Uber was growing, there was more data, they were kind of redlining. So in the last slide, we talk about the challenges that Uber had, and now we're going to talk about how Hudi overcame these challenges by supporting a couple of primitives. One is data mutability, and two is indexing. So with these two primitives, we can now do row level updates and deletes. When an update occurs, it can do an incremental pull to just pull those changes and not and not the whole table, and just update those changes to downstream applications. And I know this is kind of a lot to unpack, but we're actually in this talk, we're going to do some deep dives into some of these concepts. But I kind of just wanted to bring this in a little bit. But and in the bottom, you can look at what this incremental architecture looks like at a very, very high level, where you can just incrementally pull the data you need to update your derived or model tables and effectively have faster analytics. So this is kind of like a timeline of Hudi's evolution. It basically started in 2016 when Hudi was created in Uber with transactional guarantees, support for updates and indexes and change stream. And then around 2017, Hudi was open sourced by Uber, and they began to work on the merge on read tables, which we'll cover later in this presentation. In 2018, Hudi gained more adopters, and Hudi was officially had AWS support in EMR, and was also recognized by other cloud providers. In 2021, the Hudi's ecosystem expanded to include Flink, Spark SQL, metadata, and Kafka Connect integrations. In 2022, Hudi introduced multimodal indexing, which we'll get into a little bit later in the presentation when we talk about indexes, had further increased stability, and so on. And now with 2023, we're introducing record level index, a primary keyless data model, and so much more. If you want to learn more about the coming features of Hudi, you can go to hudi.apache.org/roadmap. You can kind of see what's coming up in their new future and later on this year as well. So now that we have the challenges Uber was facing and the inspiration behind Hudi, we can now talk about Hudi as a Lakehouse platform. So when you bring these large data applications, when you're building these large data applications, bottlenecks are inevitable, right? And as some of us know, it will require tons of time and resources to fix and optimize. So from the get-go, it's important to know your SLAs and some of the features you might need to help manage your data, but also efficiently and effectively scale as well. So in the first highlight, one of the main features to take into consideration is indexing. So write indexes provide a mechanism to efficiently locate the position where new data should be inserted or updated or deleted. And it's typically supported in multiple databases. But by maintaining an index structure optimized for write operations, the database engine can quickly identify the appropriate location and minimize the time required to do data modification. And as a result, you get faster write operation, and you reduce the latency, and you improve your overall system responsiveness. Okay, so the next highlight that we have here is, services to consider that you might need to help with data management that not all lakehouses have, right? So one is automated table services, where you can automatically cluster, clean, compact, and do all these types of things to help manage your data. So typically some of the table services are passed to the users to be run manually, and it's up to the users to coordinate and orchestrate the services alongside the ingestion pipeline. And this can be an operational overhead. The other thing to consider is to avoid full table scans on large data sets, because at scale, this is inefficient, and we'll talk about it later when we talk about the batch architecture. But all of this, in short, can lead to slower, stale, and expensive analytics. So before we talk about how Hudi is a little bit different, I kind of want to do a bird's eye view of the Lakehouse platform. So Apache Hudi is just way more than just a table format. It's only a fraction of what it is. It's a comprehensive platform designed for data ingestion and processing, and has so many range of features and services aimed for maximizing the efficiency of both write and reading data. So at the very foundational level of this platform, you have the data lake storage, right? This is where all your data resides in prevalent data formats like Parquet or Avro, and so on. And then step up, you get into the transactional database layer. This layer is where Hudi really, really shines, and it offers multiple services, including like table services, which we'll cover again later on in the presentation. Indexing, we kind of hinted at it, but we'll also do a deep dive later on in the presentation, and concurrency control, which we won't get into in this presentation, but feel free to hop in the Hudi community if you want to learn more about that. These services collectively offer significant enhancements to the data and table management as well. For example, table services facilitate the handling of data at scale. Indexes speed up data retrieval operation, and concurrency control ensures consistencies of data across multiple operations. So after your data has been successfully ingested and managed, by the previous layer, Hudi now offers the ability to connect this process data with other popular like computation engines, because Hudi has this interoperable query component where you can integrate these popular query engines to query the data. For example, you can use Trino, Presto, which are highly performant distributed SQL query engines to query the data for analytics. But by facilitating these integration, Hudi allows for efficient and advanced querying of data. So now we have this like Lakehouse platform overview and how Hudi is much more than just a table format. But now we're going to go back to this diagram and see some of the changes that some of the bottlenecks that we talked about earlier. So for example, when data is ingested, it's automatically indexed by Hudi. So Hudi automatically builds the indexes on these data files. And when you scan the file, Hudi can check to see if a key may exist in that file by using the indexing that it provides. So Hudi offers a wide range of indexes, and you can pick the right indexes for the right workload that you want. And Suda will cover that more when we get into the indexing portion of the talk. Once data is in Hudi, let's see, okay. It automatically coordinates and orchestrates the different services such as clustering and file sizing and so much, we'll again get into later in the presentation. And we'll cover that more soon. And then when the updates and deletes happen, as they typically would when you're working with CDC or streaming sources, Hudi performs these row-level changes, avoiding rewrites of the whole table. So on the read side, you can query just the incremental changes if you want, avoiding these expensive processes. And again, we'll dive into the incremental framework later when we get into that section. So part of building compute-efficient apps is having a lakehouse that can efficiently ingest, process, and manage data. Efficiency also comes with querying data, because if you can avoid, reading unnecessary files at terabytes or petabytes scale or even exabyte scale, well, why not? Because you're going to get faster analytics. And we'll get into that when we get to multimodal indexing. So we talked a little bit of Hudi. We have somewhat of a high-level architecture overview of how that helps with your framework. Now we're going to dive in and double-click into some of the table types and query types in the timeline. So some of these Hudi basics and concepts, and then we'll get into table services. So Hudi offers two different table types in order to basically store your data. One that we're going to talk about right now is the copy on write. And I think this is pretty popular if you've worked with data warehouses and stuff. But basically, as data gets written, updates to existing file groups produce a new file, a slice for that file group with some sort of timestamp. In other words, with copy on write, when you have a record that's getting ingested, it implicitly compacts every time to form a new version of the base file. This is why if you look in the diagram, you have these parquet files at different commit times. And so the write amplification is a little higher for a copy on write table, but when it comes to the read amplification, it's actually 0. And if you have, certain analytical workloads that are consistent or that are predominantly read heavy, this might be a good table type to start to work with. So I kind of want to go over some of these different types of queries that Hudi supports, and I'll cover 2 different instances, and then we'll move on to merge on reads. So let's say in the copy on write table, we have a blue box that says commit time 0, and you have your initial load, right? Or your initial ingestion. So you have inserts A, B, C, D, E, and each of these inserts are into different parquet files. So if you want to run a snapshot query, you'll get the full state of the current, like the full state of how your table looks like. So in this case, with commit time 0, you're going to get A, B, C, D, E. And if you wanted to run an incremental query or just get the changes that have happened, and then in the first initial load, you're going to get you're going to get A, B, C, D, E. It's your first commit, nothing has changed, so you're going to return everything. But it gets pretty interesting when we go to commit time 1, which is the orange box here. So in commit time 1, you have a new insert. So you have A that goes to A prime, you have B, and then you have C, and then you have a new update D prime, and then for file 3 parquet, you don't have anything. But now, if you look at a snapshot query, you're still going to get the full state of the table. So you'll get A prime, B, C, D prime, E. But now if you want to run an incremental query and just grab those changes, you can, and you will only return A prime and D prime. So this is essentially copy on write and the different query types that it offers. So now we're going to kind of talk about merge on reads and how that's different from a copy on write table. So a merge on read table is basically a superset of a copy on write table, and it still supports, read optimized queries, snapshot queries, and incremental queries. But basically what happens is that when you get updates, they go into these log files, and you can see these log files here. So your first insert will be a Parquet file. Updates will go to these log files, and then you'll run a compaction service that will compact these log files to a new version of the Parquet files. But we're going to go into why this is impactful when we talk about the query types. So let's talk about the query types now. Or actually, yeah, we can talk about that. So in the first initial load and commit time 0, you have your inserts A, B, C, D, E. So if you're running a snapshot query, you're getting the current state, you'll get everything back. You run an incremental query, you get everything back. And if you run a read optimized query, you'll get everything back. So that's pretty easy, right? It's your first insert. But now if you go to commit time 1, let's say you get updates. So A goes to A prime, D goes to D prime, and everything else is the same. Now, if you run a snapshot query, you'll still get the full snapshot of the MOR table, similar to a copy on write table. So you'll get the updates and the things that hasn't changed. If you get the incremental query, or you want to run an incremental query, you'll just get those changes, so A prime and D prime. But now if you want to run a read optimized query, you'll get the former state of the table where it was at the base file. So in this case, we'll return the snapshot that happened at commit time 0. And so this is the difference between the snapshot query and the read optimized query with merge on read tables. And now, you have more updates. They're going into log files, but now at time 3, you want to run a compaction service. So now let's say you have all these updates. You have an A double prime update. You have a D prime update and you have an E prime update in app. But when you run this compaction service, you're compacting all these log files to a new version of a Parquet file. But now when you want to run a read optimized query, it's going to reflect the current state of the base files, in this case, where compaction happened. So I just kind of wanted to point this out about how read optimized queries are a little bit different from snapshot queries, but also read optimized queries are only available for MOR tables. Merge on reads are really great for streaming sources. So if you need to have fast write, or the write amplification needs to be 0, this is a good option for this table type, but the read amplification is a little bit higher. And I have a table here that shows kind of the trade-offs between these two table types that you can look at later. So we talked about query types, so this is recapped over here. And now we're gonna go ahead and talk about the Hudis timeline. So Hudis timeline is pretty important. That's why I kind of wanted to bring it in here today. So Hudi maintains a comprehensive timeline of all the operations performed on a specific table, serving as the cornerstone for efficient data retrieval and compliance with ACID properties. So the timeline is an essential point of reference during the data writing process and table services, and plays a crucial role in a proper functioning of a Hudi table. So given the critical importance of the timeline in Hudi operations, for example, if there's a compaction, it's recorded on timeline. If there's a clustering happening, it's recorded on the timeline, and so on and so forth. So everything gets recorded into the timeline. And so this is why we're bringing it in here today. So basically, understanding the timeline can help enhance your understanding and capabilities of how to effectively and efficiently operate your Hudi tables. So there are a couple key concepts to understand with the Hudi timeline. All actions performed on the table are represented as instance in a Hudi timeline. And Hudi has in a directory, Hudi has a hidden folder called the .hudi folder. And this is where all the instances are maintained. So a Hudi instance contains 3 different things: actions, which is like, if you have a commit coming in, that's an action. If you have a clustering happening, that's an action. There are states, that's the second thing. Each action or each instance can be in a different state, and then there's an instant time of when that happens. So breaking that down a little bit more, an instant action indicates the type of operation performed on the table. For example, one action you can have is a commit, which represents a write, that's happening to a copy on write table. Now, the second thing we talked about was a state. So a state is an instance that can have an action, and each instance can be in various states of where they're at in their action. For example, I can have an instance that has a commit type action, but it can be in this can be in 3 different states. One is a requested state, the second is an in-flight state, and the third is a completed state. So a requested state denotes that there's an initiation of this action. An in-flight state means that this action is in progress, and a completed state means that this action is completed. So until the operation reaches the completed state, it is viewed as pending, and read queries are actually restricted from reading or accessing any data relating to these pending operations. So when you query data, it has to be in the completed state. And then finally, the third thing we talked about was the instant time. And this is basically the logical time when a commit happens, and we use timestamp for implementing an instant time. And in diagram, you can kind of see high level what happens. You have an upstream source, you do a batch ingestion, you write to a copy on write table, and then this commit is recorded in a timeline. But then I double click into what the timeline looks like, and you can see that there's an instant time, the action, and the state. And so a batch ingestion is requested, it's in progress, and then it's finished or completed. So now we're going to transition to some of the deep dives and concepts that I'm really excited to talk about. So one of the things we're going to mention is table services. So Hudi has different built-in table services with the goal of ensuring performant table storage layout and metadata management, which are automatically invoked synchronously after each write operation or asynchronously as a separate, background job. If you're running the service asynchronously, like with writers like Flink and Spark in continuous mode, you can invoke these table services asynchronously because they share the underlying executors intelligently along with the writers. So in short, Hudi is designed with built-in table services and self-managing runtime that can orchestrate and trigger various services to optimize everything internally. And Hudi takes care of that and kind of like abstracts that from the user. So one of the features I wanted to talk about within this is small files. And I know this is a big thing when we come in and talk about like streaming data and stuff. So one of the fundamental problems with writing data to a source is having a lot of small files. And this is popularly known as a small file problem. If you don't size your files appropriately, you can slow down the query performance and you can effectively work with stale analytics. So some issues that you might encounter are, for example, reads slow down. You'll have to scan through many files to retrieve the data for a query. And again, this can slow down your query performance. Processes slow down. You can slow down, for example, your Spark or Hive jobs, because the more files you have, the more tasks you create for reading each file. And then obviously it goes without saying your storage can increase. And I mean, when you're working with a lot of data, you have to be efficient in how you use all resources, including storage resources. It might not seem visible when you're working with small data, but it's best practice to be diligent about how you manage your resources as well. So now I'll actually now pass it to Sudha to kind of do a deep dive into how Hudi does file sizing. Sudha?
Yeah, thanks, Nadine. Can you go to the next slide? Yes, thank you. Yeah, so you can manage file sizes during ingestion through Hudi's auto-sizing capability. This solution adds a little latency during ingestion, but it ensures that read queries are always efficient as soon as a write is committed. If you don't manage file sizing as you write, and instead try to periodically run a file sizing cleanup, your queries can be slow until up to that point where that periodic cleanup has been performed. So let's dive into how this file sizing works. The file sizing feature tries to bin pack inserts into the identified small files. There are few key parameters that control the file sizing algorithm. The max file size. This is what you say Hudi. Say this is my intended file size. These are the sizes up to which my data files can grow. Small file limit. This is what you indicate Hudi to say consider all these files which are less than this limit as small files to be bin packed later. And then the other config can be number of insert split size. This is basically the number of inserts that can be grouped into a single partition. This has to match the number of records in the file. Hudi can intelligently detect this as the commits go through by determining your max file size and the average record size that it has seen historically. And it can auto infer this on an ongoing basis. So coming back to the diagram here, assume that this is the layout of the data files for a given partition. When a new write happens, initially updates and inserts are identified by looking up the index to tag the incoming records. After that, for each partition path, the eligible small files are identified. Here, the small files will be files 1, 2, 3, based on the 100 MB small file limit. And once the small files are identified, Nadine, can you go to the next slide, please? Once the small files are identified, the incoming inserts are assigned to them so that they are built up to their full capacity. So here, for example, the file 1 will be assigned 80 MB more worth of inserts, and file 2 will be filled 40 MB more worth of inserts, and file 3 will take in 30 MB more worth of inserts. So we see that the small files have been packed up until this point. Next slide, please. Let's say you have remaining inserts that are unassigned. Now, like we discussed early on, based on the insert split size, Hudi is going to assign the remaining inserts into new file groups up to the maximum file size limit of 120 MB. So in this case, for example, if we had 300 MB worth of inserts more, and assuming each record is like 1,000 bytes, then Hudi is going to create 3 more files to bin pack and make sure those are all assigned to new file groups. And all of this file sizing algorithm kind of keeps running as part of your ingestion continuously to keep your table in an optimized state. So yeah, Nadine, back to you.
Awesome, thanks. So the next thing we want to cover is indexing. We've kind of hinted it throughout earlier in the presentation, but this is where we're going to kind of dig deep into some of the indexing stuff that Hudi offers. So Hudi has an efficient write index system, which significantly boosts, write performance as well as read performance as well. And these indexes facilitate quick location of records during writes, ensuring efficient and accurate updates or inserts when you ingest data. The indexes prevent the need to conduct, for example, full table scans during data modification, which can be time-consuming and resource-intensive. And so now with Hudi's indexing mechanism, you can map incoming records to their locations in the data lake, right? This is really new because data lakes typically don't have this, right? So allowing for rapid or direct updates to existing records. Also, these indexes ensure minimal amount of data shuffling during the write process. So by streamlining the write path, Hudi's indexing capabilities play a crucial role in enabling fast and incremental data processing. Again, we'll cover that later, making an optimal solution for large-scale data sets that need real-time or near real-time analytics. So this is one part. So write indexes are really for write performance, but now when we get into multimodal indexing, which I'll talk about now, this is where we talk about how write and read performances are improved. So Hudi has a multimodal indexing strategy as well, and it's an integral feature that enhances both write and read operations. So there are 3 indexes that are part of the multimodal index. There is the Bloom index, there's the Colstat index, and there's a file index. The Bloom index checks to see whether a record exists in a file group. And if you work with different types of storage systems and stuff like RocksDB, you're pretty familiar with this. Then you have the Colstat index, which helps filtering files and data skipping to improve reads. And then finally, you have the file index, which improves the file listing performance. If you're definitely working with like large scale data. So now I'm going to pass it back to Sudha to do a deep dive on not only in the write indexes, but the multimodal indexing as well.
Yeah, thank you. Next slide, please. Yeah, so I can think of indexing like Nadine described. Just to recap, indexing is just like a widely employed technique in database systems. You can think of it like how you refer to the index page at the end of the book to help you locate information quickly. These sort of techniques are used to reduce the I/O cost and improve query performance in data systems. There are well-known indices in the industry, like hash-based index, bitmap index, primary index, secondary index, and so on. Most data systems do come with some indexes out of box and let users add additional indexes based on their own requirements. Hudi also follows the same path. Next slide, please, Nadine. So before exploring what indexes Hudi offer and where they can be leveraged, let's quickly take a look at high-level idea of how effective these indexing can be. Let's say here in this diagram, we have two pictures. On the left is a table without no notion of indexing, and the right table employs indexing. Let's assume that the white blocks are the data files, and the yellow blocks are the writes coming in, right? So here we have almost 8 cross 25, 200 MB worth of updates coming in. And without indexing, there is no way to say which of these updates need to go to which of the data files. So it becomes essentially an n cross n problem. So what here would happen is like every 100 MB data file here has to be merged with all of the 200 MB updates to process the updates, even though it doesn't belong, not all of them belong to that data file. So leading up to a merge cost of 1,200 MB. And on the contrast, I mean, if you can think of this at scale and happening for every batch of writes coming in, and as the files, like as the table grows in size, right, this can be pretty expensive. On the contrast, if you take the diagram on the right, which implies indexing, now we are narrowing the scope to route the updates only to the data files to which the original records were present. So here, the 100 MB data files need to be merged only with the 225 MB blocks, which is like 50 MB, to process the updates. So that effectively reduces the merge cost to 600 MB. By no means this is not like a benchmark, but it's a high-level illustration of how effective indexing can be to fast process updates and deletes. So with that, let's quickly dive into the different types of indexing and where they can be used. We have these are the current indexes, and much more are coming in the upcoming releases. But going over them quickly, we have a Bloom index, which employs a Bloom filter that builds out of the record keys and is neatly tucked into the footer of the Parquet files. It offers APIs for min-max pruning of the queries and range pruning based on the interval. And it is best for use cases where there are like late arrival of data, such as fact tables. You can think of e-commerce sites or ride sharing or transactional tables, which are large in volume, and they grow. They are like ever growing with random updates on more recent data partitions. But there can also be long tail updates like the late arriving data, right? So in these cases, Bloom Index work really well because of the range pruning that they offer. Bloom Index can also work for clickstream or log ingestion type of IoT sensor type of use cases where the volume of data is high, and mostly those are append only use cases, but still need deduplication because of the duplication that can come from any of the upstream systems. So they tend to. This is also a place where Bloom can work fine. We can also leverage HBase index for this type of data, but the sheer volume can make it expensive because of the need for storing those much in the HBase. Like HBase index is basically the mapping from the record key to the file group is placed in an external HBase system, and this definitely includes an operational overhead of managing HBase apart from your other systems. Whereas HBase can be suitable for workloads that are like really random updates and deletes that are spread across the table. The volume itself might not be high on the updates, but they are sparse and spread across the table. Like you can think of dimension tables where something like user profiles or merchant info and things like that, where they cannot be really partitioned on there is no good field to partition these data on. And we cannot use like the primary keys are usually random UUIDs that do not yield sorting properties. So the Bloom index might not be a good fit because of the lack of sorting properties, and it can yield a lot of false positives. So those are the type of workloads where HBase index shines really well. We have an upcoming record level index in 0.14.x, which goes above the HBase index by eliminating the need to maintain an external system and kind of process these random updates and deletes that are based on like random UUID type of keys. there is one more index called simple index, which is kind of an in-memory index that just does a lean join between the incoming writes and the record keys that are extracted out of the storage. That is very well suited for use cases where it can also be an alternative for HBase where you don't have to bring in an external system, and the Bloom indexes don't really work. Then we have bucket indexes, as the name suggests. The bucket indexes are introduced to bound the index lookup time by O of 1, like using a hash algorithm. That way, the record key can be deterministically mapped to the buckets, either a static mapping of buckets or like a dynamically growing buckets. And those are the variants of the bucket index and the consistent hashing bucket index. With that, while these indexes that we described, can you go to the next slide, please? While these indexes that we described previously help on the write performance, like Nadine described, I want to switch gears and talk about the multimodal index, which is an integral feature for Hudi. The multimodal index is basically helps optimize both read and write performances. Let's see how that helps, right? Like when it comes to query performances, right? Like behind the screen, what happens when a query executes is the first step is to fetch metadata, then do the query planning, do the optimizations, and then do the eventually get the scan the data, right? So the first step there is fetching metadata, and fetching metadata becomes the key step to improve the query performance, and that's what we're trying to achieve with the multimodal indexing subsystems. Although indexes are not new to Hudi, we have featured this in a way that in future, any new indexes can be added to the subsystem without worrying about building the framework itself. By that, I mean, Hudi already has the platform for adding new types of indexes, and without having to develop the interface between that index and other table services and stuff like that. Those are already in place, and that's why this is a subsystem. That's why it's called as a subsystem. And why we call it as multimodal there are various ranges of indexes here. There could be coarse-grained ranges, indexes like Bloom index, and fine-grained record-level index. Just like databases, the indexes can be built alongside the ingestion without having to block the ingestion or compromise it whatsoever. That is also a powerful feature of the multimodal indexing subsystem. Even better, the indexes can be dropped and rebuilt anytime. So with that, I'll move to the next slide, please. I'll skip over these in the interest of time, but these talk about different multimodal indexes. I have linked resources there that can give more details on how some mini micro benchmarks were performed to kind of highlight the impact of these multimodal indexes. With that, I think back to you, Nadine, for the next topic.
Yeah, thanks, Sudha. So we had a great deep dive on indexing, and it's been kind of an integral part of this talk. So I'm glad we covered that. The next thing that we want to cover, and this is the last service we'll cover, is clustering. So in data lakes and warehouses, one of the key trade-off is between write speeds, which can help with data freshness, and query performance. So data writes are faster with small files because since data is processed as soon as it's available, right? And you can avoid this intermediate aggregation step to combine smaller files to larger ones. But if you have a lot of small files, like we talked about during the file sizing part of this talk, you can degrade query performance because, in particular, small files cost more disk sticks and can slow down compute in downstream applications. So I won't go into that too much, but with the clustering service, it kind of accomplishes a couple of goals. One is you can decouple file sizing from ingestion into a separate table service where small files are combined to larger ones without impacting write speeds and data freshness. And the second thing you get is you get improved query performance because you're reorganizing the data layout through certain techniques, like you can specify how you want to sort a column, or what type of strategy you want to sort on and things like that. So now I'll pass it to Sudha to kind of do a deep dive into Hudie's clustering service.
Yeah. Thanks, Nadine. Let's discuss more details on how clustering can actually help query performance. Yeah, okay. So here on the top, we have this unclustered table. We have about 10K Parquet files in the table. And then let's assume that we have a select star query from the table and has a filter on a session ID equals 1, 2, 3. Let's say if it's unclustered and this session ID is scattered all over the 10K files, right? So this is a known problem. So the query planning would get back to say, oh, scan all the 10K files and then filter based on the session ID. On the reverse, let's say if we had clustering in place, what would happen is the initial 10K files would go through like a clustering, and the clustering would produce, let's say, 1K files sorted based on the session ID. And now for the same query, based on stats and predicate pushdown, the query planning can get back to just like one or maybe few files depending on the session ID volume, but that already produces 100x speed up compared in table scan compared to the previous model. So that's the high level basic idea of how clustering can benefit. Like Nadine mentioned, we can use clustering for two different purposes. One is for file sizing, if you have like a very sensitive write latency where you cannot take in hits of file sizing at the time of ingestion, but want to defer that to a background service to do it for you. Clustering can do that. Or if you want to use clustering to do a different layout of your files to gear towards better query performance, like based on query shapes, that is also possible. So let's see how the clustering service works. Hudi uses the table services to provide the self-managing clustering, right? So users don't have to worry about the internal details. There are two steps basically. The writers schedule the clustering plan and write to the timeline. By that, what I mean is like they first identify the target data files, the file slices that need to be clustered, and generate a plan and serialize that into the timeline. Later on, the same writer or an async job can pick up that plan and execute that plan based on like a pluggable clustering strategy. For example, if you configure to say, I want my clustering to be based on few columns, then you can go for a linear sorting. Or if you want it to be like 10 or more columns, and you don't have like a hierarchical pattern to your filtering, then you can go for other techniques like space curve techniques like Z order or Hilbert kind of clustering techniques. So all these are possible, and then the same writer or the async job can actually execute that plan based on the pluggable strategy. So, and the other important thing to notice here is while the clustering is happening in progress, none of the queries will have visibility into the partially clustered data. Hudi provides this sort of isolation, and the clustering can happen async with the ingestion. So once the clustering is done, that's when the queries from that point of time will use the clustered data and see the benefit. So until that point of time, while the clustering is in progress, the partial return data are not exposed to the queries. So with that, I just want to quickly finish this by just walking through what are the different deployment models for table services in general. I'm going to use clustering service for this, but this is also pretty much similar to other table services. So the users can choose from any of these. The inline mode is the simplest in terms of operational overhead, and it just adds the table service after every ingestion. That can happen serially, but it is also relaxed in terms of the write latency. If there is no SLA on your write latency, you could do this. But if you're looking for something to run in async, then you can go for the async mode. Tools like Delta Streamer and Spark Structured Streaming can run async clustering. And then otherwise, like for example, if you have a different scenario where for some tables, even with the, like you would want to separate the resource utilization of clustering and your ingestion job, what you could do is like you could still ask the ingestion job to plan the clustering for you, but separate the execution into an offline job, such as the Hudi clustering job. Or even better, if you just want to do a one-time clustering, you can manually run that from Hudi CLI. With that, I'll pass it over to Nadine.
Thanks, Sudha. So up until this point, we talked about Hudi's internals, but we haven't really tied and what that means for your data application. So I want to talk about two different approaches when it comes to building your architecture. One is the batch processing framework, and the other one is incremental processing. So I think batch, many of us will be familiar with, but I'll cover some of these points, and then we'll navigate to the incremental processing framework. So let's take a look at this pipeline. You have various sources being ingested, and it's going through a data pipeline. And you can encounter several challenges when you're working with the data pipeline. One could be complete ETL failures due, for example, like if you're working with streaming data, you can get schema changes, or you can have some issues when you want to process high volume data. Other issues that you can have is backfilling without worrying about partial writes and rollbacks, right? So when you have a failure, you have to go back in your code, update your code, and then get it working again. So this could be a challenge that you might need to overcome. The next thing that you might experience, which is the second part of the data pipeline, when we're just ingesting data, is partial updates. So they can cause inefficiencies and high resource usage, leading to significant data latencies. So if your workload even includes, let's say, just limited partial updates, you still need to join the entire table to fetch complete records, which can be costly, even if you just did like partition level updates. And both of these challenges, right, can lead to time lag between when data updates occur and when they are reflected in your lake. And so your data freshness won't be as fresh; it'll be pretty stale. And if you need to reprocess your tables frequently, you have to, increase your resource utilization. And at large scales, reprocessing tables, let's say every 5 minutes or every 15 minutes from, let's say, every 15 plus hours, can be unsustainable when you're dealing with large scale data. So to couple with data freshness and reprocessing of tables, we inevitably have to talk about merges, which is the third part of this data pipeline. And so we know that cloud storages are append only, but if you need to update data, you have to do a full rewrite of the data file and store the updates separately and then merge it later with the original file to form a new version of the file. So you might have to do like a complete rewrite. So if you don't know how your data is laid out or how data is spread across your files, then the merging can become expensive. So let's say you have a 120 megabyte file and you want to do an update. You have to perform a full table scan to find the record, and then to reprocess and rewrite the table, now you have to perform a full merge operation. So imagine doing this at petabyte scale data for just like 100 or 120 megabyte change. This is exactly what append-only workloads look like. And now you can understand why the write amplification is so high. So coming back to Hudi's indexes help eliminate the need for a full merge because it only merges the records needed with the base file. So you don't need to do the full table merge. So it's much more efficient in that aspect. So once data passes through your data pipeline, you create your raw layer. Yay. And then, the next thing you want to do is probably create your derived tables. And this is where you probably get into another data pipeline, which you can experience potentially expensive upstarts. And we talked a little bit about derived tables when we were talking about Uber. This is exactly what they were doing. Upstarts require, a comprehensive scan to match incoming records with existing ones, resulting potentially in slower analytics, data consistencies, and more. And again, you might have to merge the updates with data existing in the table, to which we have over here. And then you might form like a new temp table over here. And at some time X, right, you'll do a complete overwrite of the table and update the derived tables from the temp table. And again, depending on how often you want to do this or how much money you want to throw at this or compute power, this can potentially lead to stale analytics. So I know we ran through this section pretty fast. I'm assuming a lot of us are familiar with some of this batch architecture, but I wanted to recap on some of the essence because when we get into the incremental architecture, it'll start to make more sense. But basically, when you're building data-driven applications and you have all these expensive processes happening, this is where you can reach to some of those challenges. So now let's navigate to the incremental processing framework. So as you can see, this processing framework, by just the looks of it, looks very simple compared to the batch processing. In contrast to the batch architecture, incremental processing allows for data sets to update without repeated data processing. So if you go back to the batch architecture, one of the canonical themes is reprocessing data, rewriting data, potentially doing full merges, things like this. But when you need faster analytics, you need to be fresher, you want to have improved efficiency, you can't be doing all of that. So this design is much more efficient and scalable for large-scale data, because you can have record level data mutations, you can have indexing that can accelerate how you update data, and so on and so forth. So the incremental architecture prides itself on incrementally updating data sets without reprocessing the entire data over and over again. And you can actually power your data lakes with these capabilities to efficiently help with data ingestion and management in order to support this incremental processing framework. So a key capability that aids into incremental processing to handle data mutations at record level is one, you can't do reprocessing on non-changing data, right? In the batch architecture, this is very different. And adding an indexing mechanism can further help to quickly accelerate how you do the updates. And we talked about indexing earlier, so I won't get into it here. But earlier when we talked about the batch architecture, we talked about a couple of ETL failures. One where there could be schema changes, which actually happens often if you're working with streaming data. So a data lake with incremental capabilities can cascade the changes to your downstream applications much more efficiently, and you wouldn't need to reprocess the entire pipeline like you would with the batch architecture. The other thing that we mentioned is ingesting high volume of data, especially if you have a peak time. This is really important. Batch processing is not ideal when you have to have fast writes, right? You have to commit the data the very second it's ingested. Data typically, settles for some time before your batch process is triggered and then it's committed to a table. Moreover, batch systems are not equipped with some sort of time synaptic or version state that's typically found in stream processing frameworks. And this is a big challenge. And we kind of talked about this when we went over Uber's challenge. When we talked about some of the two challenges that Uber was trying to solve was one, faster analytics, but two, handling late arriving data that can span multiple months potentially, right? So let's go back into some of the concepts we talked about earlier. We talked about MRR tables, and I kind of want to just quickly tie this in here with streaming data. With MRR tables, remember, we can run 3 different types of queries, but one of the queries we can run is an incremental query. Same thing with the COW table, but I'm just going to talk about the MRR table for now. But basically, with the MRR table, you can get the incremental changes just happening. So when you run an incremental query, you can specify the time range that you want and only pull those changes and get those results, and then update your downstream tables if you want. And again, when you do this, you don't have to reprocess the full table. You can just update the records that need updating because of Hudi's indexing mechanism. So in short, with indexing, data mutability support, incremental updates, you can build more efficient systems and avoid these computationally and operationally expensive workloads that we've seen in batch processes. So this is kind of tying in Hudi's timeline and other concepts with incremental updates. So in Hudi's timeline, to recap, and Sudha hit on this when she also talked about clustering, but Hudi tracks all actions, clustering, commits, whatever, performed on the table in chronological order, including any updates or deletes that have happened. And then the other thing we have is data mutability. And this allows changes for record level. This includes updates or deletes and so on. And the changes are tracked actually on Hudi's timestamp using an instant time. And to tie it again, Hudi references the timeline to know exactly where the last operation was committed and only process the changes that have happened after the timestamp. So data, and then again, going back to data mutability, this ensures that you can track which records have been updated or deleted and so on. So it's tying back into Hudi's core architecture and framework. I kind of wanted to bring this in here as a use case. Actually, true story. Sumil gave a live Hudi community sync and talked about Hudi's impact at job target. And this is actually taken from his slides, which I asked for approval. And so with Job Target, they migrated to Hudi, and this is the impact. One, their data processing went from hours to minutes. Okay, that was pretty big. The second thing that Hudi helped with is that their costs went down. Not only were they able to process faster, but they were able to get the cost down. They went from processing full tables and doing full table scans of 20 plus terabytes to just doing to basically just doing incremental updates in minutes with the stuff and the concepts and the primitives that we talked about in this tech talk. And also the cost went down 4 to 5x as well, because they were avoiding these full table computations. And then with Hudi's clustering service and file sizing feature, which Sudha kind of touched on and triple clicked into some of this, they were able to improve their query performance as well. And we have so many stories that come from Hudi community that I get people messaging me that how Hudi has impacted, and I hope to shed some light on it in future blog posts and community syncs and stuff like that. But this is a true story, and I'll share the community sync on the Data Engineer Things Slack channel when it's up later on today, because I still have to process the video. Let's talk about Hudi's distinguishable features. I'm just going to talk about how Hudi is really has been, how do you say it, like shining since 2016, like in terms of distinguishable features. So Hudi was first created for upstarts and incremental processing. We talked about that to enable faster analytics. Hudi supports record level changes. We talked about that pretty in depth and even talked about it with indexing and the incremental update. We didn't get into concurrency here. I think concurrency deserves its own tech talk, but with concurrency, you can have multi-version concurrency control and insert snapshot isolation between concurrent readers and writers. We did go over different table types and when to consider copy on write versus merge on read tables. But again, with Hudi's merge on read tables, one of the distinguishable things is that Hudi has these automated and orchestrates the compaction service that avoids the user from doing that manually. And then finally, we talked about some of table services that Hudi offers. We didn't go into all of it, but we talked about some of the main features that we see the Hudi community use. And if you want to know more about the comparisons between the different projects, there's a link down in the bottom that Kyle, who's the head of product, I think he's like somewhere in the messaging helping users with their questions, but he wrote a really great blog about the comparison. And you can think about your workloads and trade-offs that you want to consider when you're thinking about these different projects. These are resources to follow up. The Uber Challenges was taken from Vinod's Data Council talk. Since 2017, I highly recommend listening to the first 15, 20 minutes, or if not all the talk. It's pretty great in understanding the challenges that Uber was facing. We have Kyle's comparison blog about the comparison projects. You can take a look at that. We have the Hudi FAQ about incremental processing. And then we have some resources about Hudi blogs and videos that if you want to learn more, read more, kind of just understand more, you can check out those links. And I'll share the slides as a PDF in the Data Engineer of Things as well in the Slack channel. Community. We're going to wrap up pretty quickly here, but the Apache Hudi is extremely vibrant, thriving, and it's rapidly expanding. The project originated in Uber, and it's been open source since 2017. And since then, we have a wide range of big tech companies and contributors. PMC members have all contributed to a project. We have about 3,400 Slack members, over 4,000 GitHub stars, and lots of people invested into making the project better. To join the Slack community, you can scan the QR code and join, even if you just have basic questions. We also hold weekly office hours, Thursday at 8 a.m. PT. If you just want to ask more questions about this talk or other features, or just want to come and say hi, I highly recommend office hours. Me, Sudha, and other members of the Hudi community are there. And if you like and use Hudi, please give us a star on GitHub. And so I think this wraps it up, and I think we're getting close to an hour, so we're happy to do a Q&A, and I'll pass it back to you.
Yeah, fantastic. Thank you so much, Sudha and Nadine. This is a great presentation, and I personally learned so much from it. It was so much information. I was thinking, oh man, my head is exploding with all these technical details, but it was super helpful. So I see we have a couple of questions on the comments, and actually, luckily, Nadine, I think your your team, Kyle and Floyd, already answered all of them. So, so that's taken care of. So I see there's a few questions asking if there's going to be recording and slides will be available. So recording will definitely be available. So Nadine, afterwards, I'll ask you for the link for the slides so we can share with folks. If we want to revisit some of the slides information later, they can definitely do that. Okay, cool. So I actually have one question from myself. So I want to learn a little bit more about kind of the trade-off consideration when it comes to choosing an index. Because in my experience with other type of database, there's always some kind of cost when it comes to index. So I want to learn a little bit more about it on Hudi side.
Yeah, I can take that question, and better yet, I can post a link here that is a detailed blog on what indexes to employ for what type of workloads. This is a bit outdated. It doesn't cover the latest indexes, but we will soon be adding more to this blog.
Yeah, sounds good. Thank you, Sudha. Okay, perfect. Well,
thank you.
Yeah, we're already on time. So, well, thank you so much for everyone for joining. And also big thank you for Sudha and Nadine for preparing this presentation. This is super helpful. And we'll have the recording and slides available, and I'll share it both on the events and also the data engineering Slack channel. So, well, thank you guys, and have a good day and have a good weekend.
Thank you.
Thank you for having us. Thank you.
Bye.
Bye.